Simon Center. What's title of your talk? Yeah, yeah.
All right, thank you so much. Great.
Stop.
It's really good to be here. The conference has been really enjoyable and I learned a lot. I'm going to give a lecture based on a paper from 1 week ago on the archive with Shai Chester. The topic is about the dynamics of 2+1 dimensional theories, where we will be leveraging a lot of new things that people have understood about anomalies, generalized symmetries, and to make concrete predictions for one of the most important gauge theories in 2+1 dimensions. These gauge theories in 2+1 dimensions, I won't talk about actual materials today, but they have a lot of applications. They appear in materials like Herbert-Smith-Tite. They appear on the Kagome lattice with Heisenberg interactions. So there is a vast array of various applications in condensed matter, but it's also interesting just for high energy physics. It's one of the simplest quantum field theories. So we might as well try to understand it. So I won't focus very much on the condensed matter applications, just on the quantum field theory perspective and the symmetries and anomalies, SPT phases and stuff like that. So first I'll start by, also I won't be giving many references. There are many people in this room that contributed, but since it's a Blackboard talk, I will probably just give very minimal references, but you can find the complete list in the paper. So I'll start by reviewing very simple things about just Maxwell theory in 2+1 dimensions. This will help to set the stage and build some context. So this is just Maxwell in 2+1 dimensions, where my notation will be that F is dA. So little a will be the dynamical gauge field, and it's a U1 gauge field. I'll just review quickly what are the symmetries, anomalies, and the dynamics. What is the dynamics and so on. So let me just review that. So of course, what is the actual spectrum? The spectrum is of course just a single particle that moves at the speed of light. A single massless particle. Okay, so a single massless particle. It's a single massless particle, and since the photon in 2+1 dimensions has only one polarization, you can call it a scalar massless, pseudo-scalar massless particle or a vector massless particle, it doesn't matter. So it's a single degree of freedom that's massless with dispersion relation omega equals k. But there are some interesting aspects to this theory when some topology is involved. So let's understand the symmetries a little better. So there is a standard standard conserved current, which is conserved by virtue of the Bianchi identity. So the terminology is that this is a zero-form symmetry. This is a standard zero-form symmetry, which is U1, and it's denoted U1 with subscript T, where T stands for topological, because it's conserved by the virtue of the Bianchi identity. That's a standard zero-form symmetry. Another conserved current in this theory is just F mu itself. F mu is also conserved by virtue of the absence of charged particles. And that's in current terminology, this is one-form symmetry. And I'll be denoting that by U1 with a subscript 1, because it's a U1, it's a one-form symmetry. So that just means that electric charge is conserved. Electric flux is conserved. That's the old statement of the Gauss law, essentially. And this is the topological symmetry. Okay. So we can couple these symmetries to background fields. We can couple the symmetries to background fields. So the background field that couples to the topological symmetry is A mu, and the other background field is B mu nu. And now you need to write a Lagrangian that's invariant under all the gauge transformations. So what are the gauge transformations? First of all, we have this dynamical gauge field, little a. So little a has the usual gauge transformations for a dynamical gauge field. Just get this. Then capital A mu is a background gauge field. It has the usual gauge transformations for a one-form gauge field. And then we have a two-form gauge field that also behaves as usual. It transforms by a one form. So maybe I'll put one here because that's a one form. And these are zero forms. So you may start from these formulas and you can try to write an action which is manifestly invariant under all the three gauge transformations and where A mu and B mu couple to the currents, right? We need the gauge fields to couple to the currents and we need to impose gauge invariance. But you'll quickly find that you need to fix the formulas a little bit. Otherwise, there is no way it's going to work. So you have to add lambda here. And now you can almost succeed. Now you can almost succeed to write a Lagrangian which is invariant under all these transformations. So the Lagrangian would take the form -1/4 e squared. And now you will write f plus b squared plus 1/2 pi little a dA. So this Lagrangian is the best you can do. So first of all, it couples correctly in the sense. So these are the correct couplings in the sense that the gauge field capital A couples to the current, which is conserved, and the gauge field capital B couples to star F, which is also the correct answer. So this gives the correct linearized couplings, but it also includes some single term like B squared that you need to add for gauge invariance. So this Lagrangian almost succeeds in satisfying all these transformations, but not quite. Maybe those that are very quick you can see that this Lagrangian is not invariant. So this Lagrangian is perfectly invariant under the actual gauge transformations phi and omega. So it's invariant under phi and omega, under phi and omega, but it's actually not completely invariant under lambda transformations. So under a lambda transformation, the Lagrangian transforms, as 1/2 pi lambda dA. Let me just see. Yeah, that's the correct sign. Okay, and you might think that there is a way to fix it, but there is no. So there is you can show that there is no way to write a Lagrangian that's invariant under the one form, zero form, and the dynamical gauge transformations. And that's one of the simplest examples of what we call a 't Hooft anomaly. So that's an example of a 't Hooft anomaly. Why is it just a 't Hooft anomaly and it does not signify that the symmetry is violated? It's because the variation of the Lagrangian is not an operator. This is not an operator in the theory, it's a C number. So capital A is a background field. You can choose it to be 0 if you want. So the symmetry is only violated in the presence of non-trivial background fields. And that's when we say that the symmetry has a 't Hooft anomaly. Of course, everybody here knows that I'm just reviewing quickly familiar things. And so the statement is that U1 topological times U1 one-form symmetry has a mixed 't Hooft anomaly. Mixed 't Hooft anomaly, and there is no way to fix them. So when you teach 't Hooft anomalies in graduate courses, usually we have this loop diagram and it's some kind of complicated computation. This is much simpler. There are two conserved currents, and you can just classically see that there is no way to satisfy all the requirements. So how is this being fixed? So one way to fix a 't Hooft anomaly is to add a bulk anomaly inflow term that we heard about in many lectures here. So in particular here, I'll add the following bulk term. it will be useful for later. So I need to modify the action by adding some integral over some 4-dimensional bulk, M4, which looks like 1 over 2 pi BdA. So if you do that, you have paid some price because now you have some 4-dimensional manifold that didn't appear initially. But on the other hand, you managed to save the transformations. I'm just confused about the sign. So I'll just fix the sign to put minus. So you have saved the transformations, but you have introduced some auxiliary 4-dimensional space into which you need to extend all the background fields. Okay. Okay, and now what is the fate of the symmetries in Maxwell theory? So since there is a 't Hooft anomaly, there is a theorem that they cannot be both, the theory cannot be gapped and they cannot be both unbroken, let's say. But of course, here we can easily understand what's the fate of the symmetries. I'll just erase that. What's the fate of the symmetries? Sorry, are there any questions about what? If there are any questions, just stop. Okay. So what is the fate of the symmetries? So U1 topological is spontaneously broken. So I already said that since this photon has only one polarization, you can think about it as a pseudoscalar, namely a pion. So one way to interpret this photon is that it's due to the breaking of this topological symmetry. What is the order parameter for the symmetry? The order parameter is a local operator, since this is a standard zero-form symmetry. So this theory has monopole operators. Monopole operators are defined by some boundary conditions near their location x. And you can show that in this model, the monopole operator condenses in the vacuum. And you can interpret the massless degree of freedom as just the phase of the monopole operator. That's the usual Goldstone theorem, Nambu Goldstone theorem. Yeah, so that's the, I will not really have time to explain what the monopole operator is. I assume everybody knows that there are local operators that are disorder operators. So that's comment number 1. What is the fate of U11? What is the fate of the one-form symmetry? So the order parameter for one-form symmetry is a Wilson loop. It's not a local operator. So to understand the fate of that guy, we have to evaluate this Wilson loop. So let's call this distance L. So we take a probe heavy charge of charge +1 and a probe heavy charge of charge -1. We separate them by distance L and let the system evolve. And we need to understand what is the expectation value of this Wilson loop. So we know that this is just Maxwell theory. So we know what happens when we put 2 probe charges. So when we put a positive charge here or a negative charge here, the Coulomb force in 2 + 1 dimensions is 1 over r. That's the force, and it's attractive. And the energy or the potential is log of r. There is, I'll put the dimensional constants. So the energy is E squared times log of r E squared. Okay, so this is the energy in the dipole where they're separated by distance L. Let's call the distance, I should call the distance L. And the sign here is positive. It's very important, yes? It's a positive sign, and this distance is L. So the energy grows as you separate them because they attract. So that allows us to evaluate the expectation value of the Wilson loop. It gives an exponential of, let's call this direction t. So we evolve the system for time t. So you'll get an exponential of minus t times E squared times log L. So that's the expectation value of the Wilson loop. And the terminology is that one-form symmetry is unbroken if the expectation value decays like the area. Usually we say that it's broken if it decays like a perimeter. Here it's neither, it's in between because it's t times the logarithm, but it doesn't decay as fast as the area. So the terminology is that therefore the one-form symmetry is spontaneously broken. So the one-form symmetry is broken, the zero-form symmetry is broken, and the anomaly is satisfied by the existence of this gapless mode, which is simultaneously the Goldstone boson for the one-form symmetry and the zero-form symmetry. So there is a Goldstone boson for both simultaneously. Yes? Can you, Yunchin, can you say? Yes, you can define the Wilson line by adding a cosmological constant term. So that will modify the answer by lambda TL. Lambda T plus L. So there is a counter term that will do that. That will be the perimeter. That's correct. So the perimeter, depending on the sign of lambda, well, yeah, the perimeter could dominate this. However, the point is that when we evaluate, okay, so for large enough T and L, this would always dominate. So you kind of, No, of course. So what we do, so the question is how do you take the limit of large Wilson loops? So what we do is we just scale the Wilson loop. If you just scale the Wilson loop, this term eventually dominates. And so yeah, because it's super linear, it's hard. So you can add this, it doesn't really, you can add it, it doesn't really matter. This counter term doesn't change anything. Yeah.
Broken. But here you can't really, even if you add the counter term, when you take the large loop limit, it seems to go to 0. And so
Yes.
the Vev of, but doesn't that mean that it's unbroken?
The reason that I'm bringing it up is that yesterday there was a lecture where this issue came up. People were confused of whether logarithmic growth of the potential means broken one-form symmetry or unbroken. What I'm saying is that it means broken. This should be interpreted as if it's closer to perimeter than to area.
Even though there's no counter term you can do to
Yes.
make.
In general, there is no counter. Let me just make another comment. When you have a standard situation of a broken one-form symmetry, let's say at a fixed point, if you take a line operator with some funny shape, it's not going to be the perimeter. In conformal filters, the expectation values of line operators are complicated functions of cross ratios. They scale with the perimeter, but they're complicated functions. You cannot remove these functions by adding a counter term. So whether or not you can remove the dependence by adding a counter term is irrelevant, because you can never remove it by adding a counter term unless the line operator is actually the unit operator. The only line operators that actually have exactly perimeter law are unit operators. So we don't discuss them anyway. So that's not the criterion.
I see. Okay. Thank you.
Okay. Okay, so this is just to frame our discussion. This is Maxwell. Now let's get to the interesting thing. The interesting thing is what happens when we add fermions in the action. So the theory that appears in some applications and is kind of intrinsically interesting is when you have a Maxwell field coupled to a NF species of fermions. So I'm writing the Lagrangian just a little bit schematically. So in this theory, the same particle plays both roles simultaneously. It's the Goldstone for the one-form symmetry and also the Goldstone for the zero-form symmetry. Why is that possible? It's possible because the one-form symmetry and the zero-form symmetry currents are related by multiplying by an epsilon tensor. So if you know that one creates this particle from the vacuum, so will the other. So we consider this model, and we can also add mass terms, which is some general matrix. Some general matrix like that. So we can also add mass terms for these fermions, or we can take them to be massless. So that's QED. That's what's called QED in 2+1 dimensions. So that's called QED in 2+1. An important fact that Yes, that's exactly what I was going to say now. A more general version of the same theory is to add Chern-Simons terms for the gauge fields. That leads to a larger family of theories. For simplicity, I'm not going to discuss it today. So I'm going to discuss this theory where the Chern-Simons level vanishes. It's just for concreteness. Just because it's more common to find this system appearing in applications in condensed matter because they have this thing that's called a half-filling, and it leads to particle-hole symmetry. The other ones are also interesting, but I'm just going to concentrate on this one. So this one has, in the UV, the bare Chern-Simons term vanishes. It might be generated when you integrate out fermions, of course, but the Chern-Simons term in the Lagrangian vanishes. And there is a famous paper of Redlich from the 80s who showed that this choice is only compatible when the number of species is even. So only when this is even. So that's called nowadays the Redlich anomaly. So you need an even number of fermion species for this theory, for this Lagrangian to even make sense. Okay, so that's called the parity or time reversal anomaly of Redlich. Okay, so that's the setup. We have a gauge field with an even number of Dirac fermions, and we need to understand what is the infrared limit. Unlike QED in 4 dimensions, where you can the beta function is infrared free. Here, of course, this coupling is dimensionful, and it becomes stronger and stronger as you go to infrared. So the dynamics is very complicated. So what do we know rigorously? I'm going to review what is known completely rigorously and can be proven analytically, and then we'll venture into kind of terra incognita. So first of all, of course, one limit that we can understand is when this mass matrix is very big in units of E², because then you can essentially integrate out all the fermions, and you land on something that's either Maxwell or maybe Maxwell plus Chern-Simons terms that we'll see in a moment, and it's kind of standard. These limits land you on something that you understand. Another limit that we completely understand is when the number of species is huge. How big? It's a question of taste. So when the number of species is very large, we can solve the model exactly, and then we can perform some perturbative series in 1 over the number of species. So I'm just going to review what we know from these 2 limits, and then we'll try to patch up the rest. Okay. Also, to simplify the discussion, you see there is a matrix of possible masses here. To simplify the discussion, I'm just going to choose it diagonal for now. Otherwise, the phase diagram will be extremely multidimensional. So I'm just going to choose Mij to be M times delta Ij. Okay. So what is the phase diagram? So let's try to understand what happens as a function of M. And let's say this is M equals to 0. That's M equals to 0, which is very strongly coupled. But we should be able to solve the theory for very large positive M and very large negative M. Okay, so for very large positive M, we can just integrate out all the fermions, and we remain with just a gauge field. But the integration out of the fermions generates a Chern-Simons coupling by the following diagram. So you have A, you integrate out fermions, you have A. So integrating out the fermions generates a Chern-Simons coupling, which is given by K, which is plus minus NF over 2. And that's actually a very quick way to see why you have to choose the number of species to be even. If you don't choose the number of species to be even, you'll get fractional Chern-Simons levels in some massive phase, which makes no sense. Okay, so that's a quick derivation of what Redlich has discovered in the 80s. So when the mass is huge and positive, you find the plus sign. When the mass is huge and negative, you find the minus sign. So actually, I should just write it more explicitly. That's what you find, the sign of the mass. So in this limit, the infrared is a Chern-Simons, Maxwell Chern-Simons theory with a kinetic term and the Chern-Simons level NF over 2. And here it's U1 minus NF over 2. And here we don't know what's going on, right? Because it's strongly coupled. So that's one general fact that we know. Oh, by the way, this also shows immediately that this model must have some phase transition, because this is topological order. Okay, so let me just say that this is called topological order. This is TQFT. And this TQFT and this TQFT are completely distinct. They have a distinct set of lines and spins. And so that means that there must be some phase transition between two distinct topological orders. And this phase transition may or may not be second order. Maybe it's first order, maybe it's a few second order transitions. We don't a priori know what's going on in that regime. By the way, I should have said at the beginning that in principle, this can also be simulated on the lattice. There was a great breakthrough recently. So traditionally, it was hard to simulate these models on the lattice because it was hard to avoid the proliferation of monopoles. So it was hard to make sure that the Bianchi identity is satisfied on the lattice. But now people have this Villain formalism, and it's in principle possible to test experimentally or on the lattice what I'm saying. So we have this phase diagram for any and F. And another thing we can do is we can take the number of species to be very large, and then we can understand what goes on where this questions marks, when in the region where with the question marks. So we can solve it exactly even for small mass. And what you find is the following. You find the simplest possible scenario. There is a single second order transition. So that's a conformal field theory. There is a single second order transition between these two topological orders. And we know a lot about the CFT in an expansion in 1 over NF. So that's some kind of, it's a non-standard, people making contact perhaps with Lakshia's talk tomorrow. The CFT is non-Landau-Ginzburg because it describes a phase transition between two topological orders. So it deviates from the Landau paradigm. And if you ask condensed matter people who work on simulations or people from our community that work on simulations, it seems that this picture holds all the way to an F equals 4. Okay, that's the belief that this picture holds all the way to an F equals 4, and it is what it is. So there's a lot of tests of this proposal up to an F equals 4. Are there any questions about it? Yes. Yes.
What's the dispersion ratio of that?
It's just omega equals k. Yeah.
You mentioned exactly a light term. Is there any sign for that?
No, I mean, preferably the sign would be positive because this represents the word line mass of these probe charges. So you want them to have positive mass, I assume. Okay, so this is the story. Actually, an F=4 is very interesting for bootstrap, and because there is a material that's called, there is a little mineral. There is a mineral that's called Herbert Smithite. You can find it on Wikipedia. It's a nice, which seems to be actually described at very low temperatures by an F=4. So there is a mineral like that on Earth. And people are, that's one reason that people got interested in this field from the condensed matter point of view. Huh? Yes. Yes, that's a good, very good point. That's an important point. I was not going to talk about it. You are 100% correct. Yeah, there are SPT phases. So when all the masses are identical, I was going to get to it. When all the masses are identical, there is a symmetry where you can rotate the fermion species into another. So the symmetry of the system is SU and F times U1 topological, right? That's the symmetry of the system when the mass is diagonal. So there are some non-trivial SPT phases. That's not enough actually to prove. You'll see. But I wasn't going to talk about an F=4. Okay, so another very interesting case that appears in a lot of applications is an F=2. And that's the focus of my recent work. And it's the focus of a huge amount of papers from the last 5 years making various proposals and conjectures. Many of them have been, at this point, refuted by the bootstrap or by experiment. So we made a proposal that seems consistent. Okay, so why is an F=2 special? It's special because so the first point to note is that this topological order is trivial. Yeah, so this is what I'm saying is that if you study Chern-Simons theory at level 1, it's a trivial topological theory. It doesn't have anyons. It doesn't have ground state degeneracy. And it's just, it's the same as nothing. It's a gapped trivial phase. Okay, so that's, it's a transparent, it describes a transparent fermion line. So it's a gapped trivial fermionic phase, trivial gapped fermionic phase. So that's one sign that there could be something interesting going on. And we're going to try to understand what could possibly going on. So let me write the Lagrangian. So to try to understand what could be the dynamics of this in this case, I'm going to deviate from this. I'll allow the mass matrix to be a general 2x2 matrix, which is diagonal. I'll take two, there will be two masses, M1 and M2. So I'm going to discuss a mass matrix, which is M1 and M2. It's just because as you'll see, this allows to access more. It gives you a two-dimensional phase diagram, so it's easier to nail what could possibly be going on in the middle. So that's what we're gonna do. So the Lagrangian is basically the same as we had before, but now we have M1 for fermion number 1 and M2 for fermion number 2. And now that I have done that, what are the symmetries? So first of all, we still have U1 topological, which is due to the Bianchi identity. That symmetry still exists. Another symmetry is U1 axial symmetry, which acts on the fermions as follows. So U1 axial will act on fermion psi1 as if it has charge +1 on the fermion psi2 as if it has charge -1. of course, the symmetry where both of them have charge +1 is gauged. So it's not a global symmetry. And a very non-trivial fact is that there is a Z2 quotient. I'm going to explain now why that is. So there is a Z2 quotient because if you look at the local operators in this series, what are the local operators? There are some made out of fermions, maybe monopole operators. If you look at the space of local operators, if something has odd charge under U1T, namely it has an odd number of monopoles, it will have an odd charge under U1 axial. So it will have an odd number of fermions. So there is some kind of correlation between the two U1s. Okay, so this Z2 quotient will be absolutely crucial to understand the phase diagram. And the two background fields that I'll use for U1 topological and U1 axial are X and Y. So these are two U1 connections, but they have funny bundles because the full symmetry has this Z2 quotient. So X and Y will be the background fields. So that's point number one. Another thing that I should mention is that if it so happens that M1 is equal to M2, as I already mentioned to Yunchin, the symmetry is enhanced because you can rotate the two fermions. So the two full symmetry is then actually U1 topological times SU2. And there is again a Z2 quotient. So for instance, that means that the monopole operator, which carries odd charge under U1 topological, is a doublet of SU2. So in this theory, the monopole operator is a doublet of SU2. That's what this Z2 implies. Okay, and final comment, if it also so happens that M1 is equal to M2 and they're both 0, the theory also has time reversal symmetry. So there is time reversal symmetry, and this time reversal symmetry is a little weird. If you act twice with this time reversal symmetry, you get -1 times the monopole number. So let's call J the monopole number, or how should I call the monopole number? Yeah, let's call J the monopole number. So if you square the time reversal symmetry, it turns out that it's -1 to the J. So time reversal acts in a weird way in QED. Furthermore, there is a mixed anomaly between time reversal and U1 topological times SU2. So there is some additional time reversal symmetry here. It's not a direct product. That's if M1 is equal to M2. And this one is obtained if M1 is equal to M2 and further they're both 0. And it's not a direct product because the square of this gives you a generator here. And there is a mixed anomaly. There is a mixed Hooft anomaly. Okay, so these are the symmetries and anomalies of this system. Are there any questions about it? Yes. 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 For
And then the T part is unchanged?
yeah, if the number of species is larger, the symmetry group, instead of SU2, you have SU and F, and the quotient is, I'm trying to remember if the quotient is still Z2 or Z and F. I think it's Z2. I think the quotient is always Z2. I might be wrong.
For odd and F, how does
I
it
don't want to
apply?
say something wrong. I don't remember. It's in the paper, actually.
Okay.
But I do remember that the time reversal symmetry algebra is a little different, depending on whether an F is divisible by 4 or 2. So if an F is divisible by 4, it squares to -1. If an F is divisible by 2 but not by 4, it squares to -1 to the monopole number. Now about the quotient, I need to check if it's a ZNF or Z2. I don't remember.
Thanks.
Okay. So now let's go through the semi-classical limits. And then that's where the fun begins, because you have to make a guess that's compatible with everything that we've just said. Okay, so we have a two-dimensional phase diagram. So from now on, it will be in this picture. I'll use this blackboard, hopefully. So this will be M1 plus M2 a half. So the horizontal axis will be the average of the two masses, and the vertical axis will be the difference. And now we can try to play the game of understanding what's the dynamics of this theory. So remember that on this axis, we have SU2, enhanced SU2. At this point, we have enhanced time reversal symmetry. Maybe I'll put it on. I'm afraid that this picture will become so cluttered that we won't be able to see anything. But at this point, there is time reversal symmetry. I'll just write T. On this axis, there is SU2. So I'll just make it yellow. And at generic points, the symmetry is just U1 times U1. Okay. So when you analyze the semi-classical limits, you need all the masses to be big. So the masses vanish on this 45-degree lines, right? If you're on one of those 45-degree lines, there is a vanishing mass, and you cannot analyze the system using semi-classical limits. So you have to stay away from these 45-degree lines, plus minus 45-degree lines. So you can analyze here, 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 and here, but not on the lines. And also not here. So here in between, this is the small mass. So it's hard to make semi-classical computations, or impossible. So what do you find here? So you integrate out both fermions. You find a gapped phase. Here you find a gapped phase by integrating out both fermions. This is essentially what I started from. I said that it's U1 level 1. U1 level 1 is a gapped phase. But there is an SPT. The SPT is for the U1 times U1 symmetry. And the SPT is 2 over 4 pi x dx minus y dy. And luckily, this is a good SPT phase. So there is a Z2 quotient, which means that some bundles are allowed, some bundles are. This Z2 quotient means that this SPT, for instance, with coefficient 1 is not allowed, because there are some bundles that would give fractional ill-defined answers. But this SPT is defined for the symmetry group, so that's good. You land on your feet, you find a good SPT. Yeah, they're just standard X and Y coupled to minimal. So you introduce X and Y into the Lagrangian by in the following method. The question you asked is too complicated to answer immediately. So I'll tell you first how you introduce X and Y into the Lagrangian. So X is introduced like this. It just couples to the monopole current in standard normalization. And Y is introduced into the Lagrangian by making the covariant derivatives here. So they have D. There is the gauge field, because they have both charge 1. And there is Y, sorry. And for the other fermion, you have D plus A minus Y. So that's how the X and Y gauge fields appear in the Lagrangian. But because the actual symmetry is quotiented by Z2, they're allowed to have fractional bundles. So there is a selection rule, which is that if the Chern class of Y is a half integer, so must be the Chern class of X. So in equations, that means that if you integrate this curvature over a closed-2 cycle and this curvature over a closed-2 cycle, they have to agree modulo pi times the integers. So that's a selection rule that you get from the Z2 quotient. This means that there are exotic bundles for the X and Y gauge fields. And that's why not all the SPT phases that you're familiar from exist. So this SPT phase exists, but the one with coefficient 1 doesn't exist. So it's great that we land on our feet. We found a good SPT phase. Here it's gapped. and trivial SPT, no SPT. So these two limits are easy to analyze. And now, what about here? When we're in this region, there is one positive eigenvalue, one negative eigenvalue. You integrate out the fermions, and you don't generate U1 level 1 Chern-Simons term. So there is a free photon. So here we have free Maxwell. And here we have free Maxwell. That's the infrared limit. And we already know everything about free Maxwell. In free Maxwell, the monopole condenses. I told you a little bit about it at the beginning. There is an accidental one-form symmetry and a monopole condenses. So these are important facts. So this is what's known from semi-classical limits. And now we make the next. I have a half an hour.
Now you have 15.
15 minutes? Okay, good. So this is what's known from semi-classical limits. And now let me just quickly go through the history. So one important conjecture in the literature was that there is a single CFT. That's perhaps the most obvious conjecture, that all the lines go to the origin and they connect in a single CFT with some exotic properties and enhanced symmetries. That was refuted by numerical calculations. So that was the leading conjecture for some years. Another conjecture involved that there are two Goldstone boats here. That there are two Goldstone modes here. That was another important conjecture that goes back to the 80s. And that is also incorrect. You can show that this just makes no sense. So that's why we revisited the problem, because there was no proposal that made sense anymore. So I'll show you now how it can, one thing that actually works. So it's important to first understand the phase transition between free Maxwell and gapped SPT. It's important to understand what happens on this line. That's an interesting transition where a photon disappears. And similarly, we have the same transition here, here, and here. So as I told you, one way to think about free Maxwell is that it's a condensation of some monopole operator. And therefore, there is a S1 Nambu-Goldstone boson. So you can think about free Maxwell as S1 Nambu-Goldstone boson. So there is a very minimal way. There is a very minimal idea of how to connect an S1 Nambu-Goldstone boson to a gapped phase. And that is through the O2 transition. So let's just write tentatively here, O2 Wilson-Fisher. So what is the O2 Wilson-Fisher model? The O2 Wilson-Fisher model, which is also known as the XY model, is just a complex scalar field with a quartic potential and some m squared. So this model, when m squared is positive and large, sorry, there is absolute value here. It's a complex scalar field. So when m squared is large and positive, it's trivial and gapped. When m squared is large and negative, it gives an S1 Nambu-Goldstone boson from the condensation of the scalar field. So we'll put O2 Wilson-Fisher here tentatively. And this might look weird for the following reason. So this idea was not really seriously pursued because how can the O2 Wilson-Fisher model describe a transition from an SPT phase to free Maxwell? So that seems to be just incompatible with the fact that there is a counter term. So there is some story about SPT absorption that I won't have time to explain today because I want to get to the punchline. But that's a big part of what we wrote. There is actually a way, there is some mechanism that's called SPT absorption that allows this free Maxwell field to eat, so to speak, to swallow this counter term, and this is consistent. So that's an important step that I don't have time to explain. It will take at least a half an hour, 15 minutes to explain it. So, and then once you realize that putting an O2 transition here makes sense, there is an obvious way to continue. Because what happens when you glue two O2 transitions? when you glue, a very obvious way to glue O2 transitions is to have an O4 Wilson-Fisher transition. So let's explore the following proposal. This is O4 Wilson-Fisher. And that's it. So we just connect these lines in this fashion. And there are no more transitions. And we remove the question marks. So let's explore the following idea that the two O2 Wilson-Fisher models will join into an O4 Wilson-Fisher model. So you just say that you have a scalar field with 4 components instead of 2. Now, this raises some alarm bells because on the yellow line, the symmetry is SU2 times U1, not O4. So you might ask, is it even consistent to assume that there is an O4 transition where the microscopic symmetry is only SU2 times 1? Because SU2 times U1 is smaller than SU2 times U1 is a subgroup of SO4, which is basically SU2 times SU2. So you can ask, is it natural from the renormalization group point of view to have an O4 transition where the microscopic symmetry is only SU2 times U1? So in particle physics, this is known to be a natural, when people investigated, for instance, the hierarchy problem in particle physics, they ran into the exact same question. And this is called custodial symmetry in particle physics. If you want to learn about it, there is a huge body of literature. It's called custodial symmetry. Now, what does custodial symmetry mean? Custodial symmetry means a simple fact in group theory, that if you have an operator in the O4 model that breaks O4 but preserves SU2 times U1, it has to be extremely relevant. There are no simple operators that can do that. So the group theory statement is that, I'll just write it here and go back to the other, is that operators in the O4 model, which look like that. So let's consider operators like that in the O4 model, where all these indices are symmetrized because these are bosons. So these sit in some irreducible representation of SO4, where you remove the traces of rank n. If you try to decompose it into representations of SU2 times U1, you'll find that there are no singlets. In other words, an operator that preserves SU2 times U1 and breaks SO4 has to be very complicated. You have to insert derivatives, and it will be extremely irrelevant. So the emergence of an enhanced O4 symmetry is very natural from the renormalization group point of view. Are there any questions about it? Yes, I'm saying it's natural from the renormalization group point of view to have an enhanced symmetry of O4. I'll soon show you that there is already numerical evidence that supports it. I just want to patch the phase diagram and then tell you the one test that you can make. Okay. So that's why the fact that there is an O4 Wilson-Fisher model here is very natural from the renormalization group point of view because of what's called custodial symmetry in particle physics. And if you investigate what happens in this neighborhood of the O4 model, then the O4 model has some directions in which you will get O2 models when one scalar field goes massless. It has a direction which is completely gapped when all the scalar fields are massive. And it has a direction, which is the yellow line, where both scalar fields, where all the 4 scalar where the scalar fields condense, and there is SO4 symmetry. So on this yellow line, there is an S3 nonlinear sigma model. Okay, it's just because we have SO4 accidental symmetry, so it's natural to get an S3 nonlinear sigma model on the yellow line, while off the yellow line, we just get an S1 nonlinear sigma model. Okay, and there is just one more step to finish the proposal. The S3 nonlinear sigma model has an interesting parameter in the Lagrangian that we must determine. It's connected to one of the first talks in this conference. It's the theta angle. We heard about the work of from Shi Chen. There is So let's discuss the S3 nonlinear sigma model in 2+1 dimensions. So the way to parameterize points on the S3 manifolds is to use a group, an element in the SU2 group. So this is the kinetic term. So this is the kinetic term on the S3 nonlinear sigma model. But there is an interesting deformation, which is classically invisible, which is theta times gamma, where gamma corresponds to pi3 of S3. So gamma is 1/12 pi times the integral over dx dt of trace. Sorry, I forgot to write trace. Trace of d g minus 1, dg g minus 1, dg g minus 1. So the S3 sigma model has a theta angle. And when I say that there is an S3 sigma model on this yellow line, I have to specify the theta angle for a complete characterization of what's going on. So since here there is an O4 transition, and since here there is an O4 transition, the O4 transitions are just standard Landau-Ginzburg models. These are scalar fields that condense. So obviously they spit out 0 theta. Theta is defined mod 2 pi though, because gamma is valued in the integers. This integral is valued in the integers because it's the homotopy pi3 to S3. So theta is defined mod 2 pi. So here in this window and here in this window, theta has to be 0 or 2 pi because it's a Landau-Ginzburg description. It cannot spit out the theta angle. So let's put theta equals 0 here and theta equals 2 pi here. Just that's because what I'm going to suggest is that theta varies from 0 to 2 pi continuously along the yellow line. And exactly here, it hits theta equals pi at the time reversal invariant point. And an important consistency check that you can make is that if you remember, I told you a while ago that there is an anomaly between the time reversal symmetry and SU2 times U1 mod Z2. You can verify that that sigma model with theta equals pi exactly reproduces that Hooft anomaly. And furthermore, it allows to explain the jump in the SPT phase. So the final proposal is the following. I'm just gonna summarize. So our proposal for the infrared limit of QED. So our proposal for the infrared limit of QED with 2 flavors or 2 species is that it's at the point where the masses vanish. At the point, I used lower script, sorry. At the points where the masses are 0, it goes to the S3 nonlinear sigma model at theta equals pi. So what is the dynamics that drives this proposal? The dynamics is a condensation of a monopole. Exactly like we had in Maxwell theory, but in Maxwell theory, the monopole had a phase and it gave an S1 Nambu-Gaussian boson. In QED with 2 flavors, the monopole is a doublet of SU2. So upon condensing, it leads to the symmetry breaking pattern of SU2 times U1 going to U1, and therefore there are 3 Nambu-Gaussian bosons. This is in contrast to the leading conjecture from the 80s, which only had 2 Nambu-Gaussian bosons, which is actually inconsistent. So that's the proposal. Now, in the last minute, I'll just say some important consistency check from numerics. So there is some very important hint from numerical calculations of monopole operators that the scaling dimensions of monopole operators, when you do an RG flow like that, seem to be very close to the O4 monopole operator, O4 symmetric tensors. And we have in the paper a table that you'll see the numerical agreement is striking. So this phase diagram explains that numerical agreement. And another thing is that this fact that there are O2 transitions here can be understood from some dualities that have already been proven numerically. So you could say these lines, we can argue that they've already been proven to be true numerically. And the fact that there is an O4 transition has some strong numerical evidence. So that's why we believe this is the correct answer. And philosophically, we're used to the fact that monopole condensation leads to a single massless degree of freedom. Here we see that monopole condensation leads to some kind of non-abelian Coulomb phase, where the dual photon is fibered over two additional massless scalars. So you can interpret one of them as the dual photon, but the other two are kind of less familiar. So that's the end. Thank you.
Thank you for the wonderful talk. Now it's open for question and discussion.
So I'm very interested in this scenario, and I completely agree with what is happening here. My question is about the relationship with this scenario and the QCD chiral phase transition at finite temperature with two flavors.
That's right.
And in particular, you can introduce a theta term by introducing the baryonic imaginary chemical potential.
I'm not introducing the theta term. Here, the theta term pops out from the dynamics.
Yeah, but if you compare it with the QCD dynamics at finite temperature in 4D.
I understand. You're talking about some scenario where there is dynamical abelianization because of you start from QCD and then there is dynamical abelianization to U1. Is that what you have in mind?
Well,
how do you get to U1?
No, I don't get U1, but I mean.
So what's the question?
Well, if the SU2 cross SU2 is broken down to SU2 or O3, you get the S3 sigma model.
I see what
you're saying.
And
then if you further add the baryonic chemical potential, then this corresponds to the theta parameter in your discussions. And whether this tells you something about the phase transition.
Okay, so you're suggesting that at finite baryon density, this could be an effective field theory. Yes, so you're saying that QCD with finite baryon density and finite temperature could be described by this model.
Yeah,
because they both have this
phase. With each other. Or
I've never heard this idea before. It sounds interesting. I understand what you're saying. You're saying both have this phase.
Yeah.
So maybe there's an effective theory. Yeah, it's true that at finite baryon density, there is a Fermi surface. So maybe that's an effective theory around the Fermi surface at finite temperature, like it becomes 2 + 1 dimensional. Yeah, it could be. I've never heard this idea before.
Yeah. I got interested in this duality between this and the QCD in 1 + 3 dimension with high finite temperature. So probably we can discuss it later.
Yeah.
Other question?
Right.
So in your figure, it seems there shouldn't there be some symmetry if I invert all the masses, send all masses to minus themselves? Somehow on the right side, you have a gap trivial phase and left side, you have an SPT phase.
Right.
Is it a convention? Could I have the SPT on the right and the gap phase, trivial phase on the left?
Excellent question. So if there is at the massless point, the ultraviolet theory has time reversal symmetry, which means by Spurian logic that if you go to non-zero masses, you act with time reversal symmetry, it should act on the masses. Indeed, what time reversal symmetry does is it takes all the masses to their negatives. So that's why this diagram looks a little bit invariant under reflections. But if you look more closely, it's not invariant under reflections because of this. But this is a C number. That's a C number. It's not an operator. So that's the easiest way to prove that there is an anomaly, because an 't Hooft anomaly is when the invariance is violated by C numbers. So when I told you that there is a mixed anomaly between time reversal and U1 times SU2 mod Z2, the way to derive it is just from this picture. You can just see that there is no way to make you could make the diagram symmetric by adding in the ultraviolet -1. So this will become 1.
Classically, yeah.
That will become 1, and then you'll get 1 here, right? X dx minus. But then you destroy something else. What do you destroy? I said that this is not an allowed SPT phase because of the Z2 quotient. And that's standard at 't Hooft anomalies. When you have a 't Hooft anomaly, you can say, I destroy time reversal symmetry, or you can move the anomaly to destroy U1 times U1 mod Z2. So there is no way to save everybody. Either time reversal is violated or U1 times U1 mod Z2. Whatever you do, the theta equals pi sigma model here fits the anomaly, so it's consistent.
But on the other hand, if you send only one of the masses to minus itself, then your figure doesn't
That doesn't
have any
that there-
symmetry. It's 90-degree rotation, right?
Yeah,
It's
there is
the
no such
Fourier
symmetry,
series.
obviously. You see that takes
Yeah, of
a
course,
number.
it's not time reversal.
Yeah, because it takes a free Maxwell phase to a gapped phase. Yeah.
Other question?
These operators, which are complicated to construct with derivatives also. I think you say they respect all four, but they respect.
Yeah, you need-
You say relevant or irrelevant?
Irrelevant.
Okay.
Irrelevant.
Thank you.
So you can ask, what do they do for the sigma model? These complicated irrelevant operators. What they do is that it's a famous fact in mathematics that S3 has a family of metrics, which are SU2 times U1 invariant, but not SO4 invariants. So it just a little bit squashes the S3. So here I just wrote a simple round metric on S3, but actually we expect that there will be a little bit of squashing because of these highly irrelevant operators.
Thank you.
I also have a question. In the language of O4 Wilson-Fisher theory, so what kind of deformation operator is active to go to S3 sigma
Here?
model? Yeah.
Here?
Yeah, from here to, so here, I think we have a
This is the O4 point. So,
point and
so this is the O4 point. So you start from this where phi is a O4 vector.
yeah.
So
Yeah.
So this is a phi, let's say this is phi to the fourth. Then you have M1 twiddle squared phi. So you split the four-dimensional vector into two complex complex vectors, two-dimensional vectors, phi 1 and phi 2. So now you can do a little exercise of analyzing the phase diagram of the O4 model as a function of two mass parameters, M1 twiddle squared and M2 twiddle squared.
Yeah.
So let me draw it. So here's the O4 point.
Yeah.
You'll get two lines like that. So here there will be S3. Here there will be gap. And here there will be S1.
Yeah.
So when M1 twiddle squared is equal to M2 twiddle squared and they're both negative, then you get S3.
Yeah.
Because you have SO4. So.
Yeah.
So you see this phase diagram? Now just move it in your head here.
Yeah.
So you see, it's the same.
Yeah. Okay, thanks.
So
Other question? Okay, if not, let's thank the again.